Yes, welcome once again to my channel and welcome once again to physics optional class, and we will move on towards our next topic, which is packing fraction. Okay, so there might be some sound disturbance today. Okay, there might be some sound disturbance, but bear with me. Let me reduce the speed. Okay, so due to climate change and all those things, already the winter is gone in the month of January itself. Okay, so this is the effect of climate change. So, packing fraction, packing fraction. Now, packing fraction is defined something like this: that we will first take the isotopic mass, okay, isotopic mass, and we will subtract the mass number from it. We will subtract from it the mass number, and as soon as we subtract the mass number, we will again divide it by the same, that is mass number. Okay. Now, do not call it mass defect. Okay, do not call it mass defect, it is very different. Okay, so packing fraction is the ratio of difference of actual isotopic mass of the nucleus and its mass number. Okay, so you can write that it is the ratio of difference, ratio of what, ratio of difference in the isotopic mass and mass number. Okay, ratio of the difference of actual isotopic mass of nucleus and its mass number with its total mass number. Okay, so you must know this, you must be aware of this. Let me take you an example of this. So it is symbolically how it is represented. Symbolically it will be represented something like this. Okay, mza means it is the isotopic mass, and a is your mass number, and divided by mass number. So what is this? This is basically symbolic representation. Now now you know this very well, that for iron we have atomic number 26, mass number 56, and isotopic mass is basically your 55.93494. Okay, in atomic mass unit. Okay, so I will put this value in this formula while finding the packing fraction. Suppose I am told that find out the packing fraction of iron, find out the packing fraction of iron 56. Suppose I am told this, then what I will do, I will basically put this value in the place of this. Means over here I will put 50, 55 point etc etc in the place of this I will put, and in the place of this I will put the mass number. What is the mass number? Clearly the mass number is 56, so I will put 56 over here, and this is also mass number, so 56 will come over here. So negative packing fraction. Okay, negative value will come out. Okay, so this isotopic mass can also be called as actual mass of the nucleus, right? This isotopic mass which has been written over here, this isotopic mass can also be called as actual mass of the nucleus, because actual mass is equal to the isotopic mass, right? Isotopic mass and actual mass are same by definition, right? So you can also write over there that actual mass of the nucleus minus mass number divided by mass number. Okay, now packing fraction may be negative, 0 or positive. Packing fraction may be of three types. Okay, packing fraction may be negative, 0 or positive. A nucleus for which a nucleus a nucleus for which Now over here, when I had found out the packing fraction for Fe56, iron 56, when I found out the packing fraction for iron 56, I got negative value. Okay, but it's not necessary that I will always get negative value. I might get 0 also, and I might get positive value also. It's not necessary that I will always get negative value. So a nucleus for which A, M, Z means the isotopic mass is smaller than atomic mass number implies that your packing fraction will be negative. This is very much common sense, right? You will put it in the formula. If suppose in this formula, if suppose your isotopic mass is less than the atomic mass number, then packing fraction will be negative, right? If your isotopic mass is greater than the atomic mass number, then your packing fraction will be positive. And in case if your atomic if your this isotopic mass is equal to, suppose, okay, if your isotopic mass is suppose equal to your atomic mass number, then what will happen? Then packing fraction will be 0. By the formula you can clearly see this thing. So a negative packing fraction represents a more stable nucleus, right? A negative packing fraction will represent a negative packing fraction. Over here, this numerator, if it is negative, then clearly mass has been lost in the formation of such a nucleus, right? If suppose you are subtracting the mass number from the isotopic mass, then clearly mass is lost in the formation of the nucleus because it is coming out to be negative. Suppose if it is coming out to be negative, then clearly your isotopic mass is less than atomic mass number, and if your isotopic mass is less than the atomic mass number, then clearly mass has been lost in the formation of that particular nucleus. Okay, so as mass has been lost in the formation of that particular nucleus, so that nucleus will be in general more stable. Okay, so F is negative. So a negative, let me write over here, a negative packing fraction, a negative packing fraction represents, a negative packing fraction represents a more stable nucleus as during the formation of such a nucleus, during the formation of such a nuclei, more energy is released, right? More energy, that is mass has been lost according to the formula delta E is equal to mc square. Mass has been lost as a result of the formula Einstein mass equivalence relation. According to that formula, delta E is equal to mc square. So suppose delta M mass has been lost during the formation of the nucleus, so that delta M appears in the form of difference between isotopic mass and atomic mass number. Okay, so your packing fraction will be basically negative in the case when mass has been lost during the formation of nucleus. So this is the thing. So more energy is released during the formation of such a nucleus. For example, examples of nucleus with negative packing fraction are as follows. Suppose the same example I take iron 56, then what will happen? Its isotopic mass, you all know this very well, that the isotopic mass of this particular entity is like this. This is the isotopic mass of this iron 56, and your argon 1840. Okay, this also has a negative packing fraction because its isotopic mass is basically 39.96238 U. You don't have to remember these values. Okay, these particular values you need not remember. Keep this thing in mind. Need not remember these particular values. You need not remember them. So So energy is released during the formation of these, as these have negative packing fraction. Okay, and in the examination whenever numerical will be asked, based on this particular value in the blue box will be given to you. Okay, this particular value in the blue box will already be given to you whenever you solve any numerical in the examination. So this isotopic mass you need not remember uh, any element. Okay, for the nucleus of any element you need not remember the isotopic mass, because the isotopic mass is a long complicated number. So you need not remember that. It will always be given in the numerical which we have to solve. Okay, now this is the point number 1. Now the second point, for nuclei with F equal to 0, now very few nuclei are there with F equal to 0. For nuclei with F equal to 0, your isotopic mass will be equal to atomic mass number. Okay, so now the example of these are very few. O816 is one such example, C612 is one such example. Okay, then H11 is one such example. Over where the packing fraction comes out to be 0. Packing fraction, how it comes out to be 0? Your this value isotopic mass, okay, your this isotopic mass becomes equal to the mass number. So when you subtract these, you get 0, and 0 divided by anything is 0. So in that case you will get 0. So in these particular 3 nuclei, others also might be there, but these 3 are the most common examples. You have to remember these examples. Okay, you have to remember this nuclei. So write a note over here. Remember the nuclei. Remember the nuclei with 0 packing fraction value. Okay, you have to remember this nuclei with 0 packing fraction value, because you will need these again and again. So keep these 3 nucleus in mind. Keep these 3 nuclei in mind. Now some nuclei will be there. Okay, some nuclei will be there for which positive packing fraction may be there. So nuclei with positive packing fraction has clearly your isotopic mass will be clearly greater than atomic mass number. So examples of such nuclei, there are examples. Your deuteron, okay, this is what your deuteron. This is your deuteron. So deuteron has mass, isotopic mass equal to 2.0144. So clearly this 2.0144 is clearly greater than these two. Okay, and then you have uranium 92 238. This also has your isotopic mass equal to 238.051 atomic mass unit. Okay, over here also it will be in atomic mass unit. So and this is mass excess case. Okay, you can clearly see this, that over here the mass is in excess. The mass is in excess. So packing fraction versus atomic mass unit, the graph. Now the question arises, if we plot the graph of packing fraction versus atomic mass, not atomic mass unit, atomic mass number. Okay, if we plot, okay, so right over here, plot of graph between packing fraction F and atomic mass number A. So plot a graph between packing fraction F and atomic mass number A. If we plot a graph, then how does it look? So it will look something like this. Okay, all these things are given in your books, so you have to clearly mug up all these things. Okay, so you will mug up by understanding, so you will be in benefit. If you mug up something without any mind, then it is very difficult to remember the things. But if you mug up anything by understanding the logic, so that things get into your mind deeply. Okay, those things get into your mind deeply. So this is how the graph looks like. If I draw the perfect graph, then the perfect graph looks something like this. Although the shape was not correct, which was seen over there. The shape is something like this. Okay, the shape is something like this. Okay, so on this particular graph, the packing fractions of these nuclei are out of the graph, He4. Okay, then C12 are outside this graph. C12 is also outside this graph. Then O16 comes over here. That is also outside of this graph, outside of this curve. Okay, so that means that they should be having the value over here, right? Because the atomic mass over here, what is there? Atomic mass number is there, and over here packing fraction F is there. So if O16 lies over here, okay, so 16 atomic mass number must be over here. So as the 16 atomic mass number, if we try to find out the plot, then the packing fraction must have been greater, right? Packing fraction must have been greater, but the packing fraction is little bit small for this. Okay, as compared to the graph, the packing fraction is smaller for this nuclei O16, C12 and He4. So clearly these He4, C12 and O16, okay, these three nuclei are more stable than expected, are more stable than expected. So these three nuclei He4, C12, O16 are more stable than expected. Okay, so just note down some points over here. Okay, so note down some points over here. Packing fraction is high for nuclei of smaller mass number. Okay, packing fraction is high for nuclei of smaller mass number. Packing fraction is high for nuclei of smaller mass number except O16, C12, He4. Okay, so packing fraction is higher for nuclei of smaller mass number except these three. Okay, except these three, I already told you just now. Okay, so for these three nuclei, the packing fraction is relatively small. That means extra stability is there. Okay, so but then it decreases rapidly with increase in mass number. But then it decreases rapidly with increase in mass number. Okay, so it decreases rapidly with increase in mass number. For low atomic mass number nuclei, for low atomic mass number nuclei corresponds to this region, this particular region. And in this particular region, as the atomic mass number increases, there is a rapid fall in the packing fraction. Means the stability rapidly increases. Lower is the packing fraction, more is the stability. So the stability rapidly increases in this particular region. Okay. So that thing has been written over here, but then decreases rapidly with increase in mass number. Means stability increases, packing fraction decreases. So you have to basically discuss the graph after passing through a comparatively flat minima. Okay, so see over here, after passing through a comparatively flat minima, it is a comparatively flat minima. What is a steep minima? Steep minima is like this. Steep minima is like this. Oh, this is comparatively flat minima. Means it is taking a longer area, larger area. Okay, so it is a comparatively flat minima. So after passing through a comparatively flat minima, so let's write over here. After passing after passing through a comparatively flat minima, it starts increasing slowly but steadily. It starts increasing slowly but steadily. It starts increasing slowly after passing through a comparatively flat minima. After passing through a comparatively flat minima, it starts increasing slowly as compared to this decrement. As compared to this rate of decrement, this rate of increment is slow, okay, but steady, like a straight line almost. Okay, so that thing is there. So slowly but steady. A negative packing fraction, what does this mean? So let me write the point over here which I already told you. A negative packing fraction, a negative packing fraction means that there has been a conversion of mass into energy during the formation of the nucleus. So negative packing fraction means that there has been a conversion of mass into energy during the formation of the nucleus. I had already told you this, because the isotopic mass is less than the atomic mass number. So the isotopic mass is less than the atomic mass number. So clearly it implies that some of the mass has been lost in the form of energy. So some of the mass as it has been lost in the form of energy. So clearly from Einstein energy equation, it is an exothermic process, and as it is an exothermic process, so the nucleus is more stable. Okay. This implies exceptional stability. This implies exceptional stability of the nucleus. This implies exceptional stability of the nucleus. Exceptional stability of the nuclei. Now a positive packing fraction will imply that it is a mass excess case. Okay, a positive packing fraction positive packing fraction, and hence mass excess. Implies that the nuclei are somewhat unstable. So positive packing fraction means mass excess implies that the nuclei are somewhat unstable. I had already told you this. Positive packing fraction just means that the isotopic mass is greater than the atomic mass number, and as the isotopic mass is greater than the atomic mass number, so clearly some of the energy has been converted into mass. That's why it is a mass excess, and as it is a mass excess, so it is an endothermic process, because energy must have been supplied in the formation of such a nucleus, so that some of the energy is converted into mass. So it is an endothermic process. Okay, so it implies that nuclei are somewhat unstable. So this is the thing. Now we will move on towards the binding energy per nucleon, but about that we will learn in the next class. So till then, अपना ख्याल रखें. We will learn about binding energy per nucleon in the next class.